Mars, our next-door neighbor in the solar system and perhaps the most thoroughly studied of all the planets that orbit our sun. Besides Earth, of course. According to NASA, Mars is currently home to 6 landers, 3 rovers, 1 additional larger Mars Science Laboratory, and a whole host of orbiting probes. Although many of them are no longer operational, and in fact some never were, the data each unearthed has helped to drive our understanding of Mars as it is now, and perhaps as it once was. So, when we say that we're looking for life on Mars, we don't really mean little green people, although that would be incredible. What we are really looking for is evidence of life. Things like liquid water, organic molecules, hydrocarbons like methane and carbon dioxide. Things that living things leave behind. Each rover and probe on Mars is specially equipped to perform an array of experiments, to test the soil composition, sample the atmosphere, or simply take as many photographs as possible. Of the signatures that scientists are looking for, water and methane are 2 of the most significant. Pretty much every living thing needs some quantity of water to survive, even if that quantity is infinitesimally small, and only comes around every other year or so. Mars, as we know it today, is a very cold, very dry, rocky planet, approximately 1/6 the size of Earth. Sometimes called the Red Planet, Mars appears red due to iron oxides in its volcanic soil. It has a much thinner atmosphere and less gravity than Earth. However, the Mars of today is significantly different from the planet that existed more than 4 billion years ago. Early Mars had a dipolar magnetic field similar to the one that Earth still possesses today. This dynamo helped to shield the surface of the planet from harsh solar radiation for approximately 600 million years before it dissipated. Young Mars was also subject to fluctuations in its axis of rotation, referred to as its obliquity. A high obliquity rotation increased the amount of solar energy that could reach the planet, causing climate fluctuation and contributing to a recurring cycle of flooding events. The evidence of liquid water on Mars can be seen in the distinct geological structures that it left behind. Structures that can be clearly seen in images captured by probes and rovers on the planet's surface. Deep valleys, large plains that resemble ocean basins, and large ridges that are believed to have been formed from sediments deposited by water flows are clearly visible in modern images of the small planet. In addition, Mars' soil itself contains evidence of global water flows. The unique chemical composition of the soil on Mars is very likely the result of aqueous reactions between the water flowing above and the mineral sediment below. In addition to liquid water flowing across its surface, young Mars was also characterized by severe volcanic eruptions that contributed to high outgassing and development of an atmosphere thick with water and carbon dioxide. The frequency of meteoric impacts was also higher at this time, and the resulting heat events from these impacts were more easily survived thanks to the surface oceans that were there at the time. What we know about Mars' past suggests that it may indeed have been suitable for life, given its similarity to Earth in a number of environmental factors. However, at some point in its history, Mars lost its magnetic field, and constant bombardment by meteorites caused aggressive drying and cooling to occur on the surface. This in turn caused the global oceans to either freeze, sublime, or sink into the subsurface of the planet. Although the surface of Mars today appears extremely hostile, there are still a few environmental niches that could potentially be habitable. According to a 2019 paper, there may be windows of time when a specific Martian niche becomes habitable. The arid nature of the soil on Mars' surface supports the presence of perchlorate salts, which are highly hygroscopic. Under the right conditions, these salts can form highly saturated brines by absorbing water from around them, and may be so highly concentrated that the resulting solution remains liquid even at Mars' lowest temperatures. Environments with very high salt contents do exist on Earth, and many specialized microbes are able to colonize them. Bodies of water such as Hot Lake in Washington, Bosque Lake in British Columbia have been previously proven to support highly salinotolerant, epsotolerant, and psychrotolerant microbial life. While these lakes are generally highly concentrated in chloride salts such as sodium chloride, in comparison to the sulphate salts that primarily exist on Mars, the two environments share enough similarity in other qualities to support speculative conclusions about Martian habitability. To investigate how microbes might be able to colonize these kinds of eutectic solutions that may at times exist on Mars, scientists at Wichita State University grew microbes isolated from Hot Lake, Basque Lake, and even the spacecraft assembly facility at JPL in eutectic and near eutectic solutions of magnesium sulphate. A eutectic solution is one that contains the maximum amount of solution at its lowest temperature possible without precipitation, meaning without any of the solute falling out of solution. Under these Mars-like conditions, isolates of Halomonas and Nestorenconia grew, albeit significantly more slowly than they had at lower salt concentrations. This demonstrates that microbial growth may be possible under the environmental conditions of Mars. Even if these conditions arise only infrequently on the planet, microbes may survive in the interim by entering a state of cryptobiosis, to wait until the environment can sustain growth once more. This is a phenomenon we know happens on Earth with nematodes and creatures like tardigrades, also known as water bears. This study represents only a small portion of the research being done into environments that have been deemed Martian analogs, as many more are being performed each year. Research may be done in places like McMurdo Dry Valleys or high volcanic mountain soils. As our technology on Earth and beyond the atmosphere improves, we will likely continue to learn more and more about the small red planet that is just next door.